Uh, um, we're continuing with our discussion of bosonic theories on a circle, and so we've completed our discussion of the theory, the bosonic theory on the circle, with radius twice or equivalently half times, square root 2 times or equivalently 1 by square root 2 times the self-dual radius. Right? We said alpha prime equals 2. The self-dual radius is r is equal to square root 2. And over the last 2 or 3 lectures, we were discussing the theory with, at radius r equals 1, equivalently r equals 2. That was the theory which was dual to the free fermions. Okay? Now, as I said at the end of the last class, if you have, there's a particularly special radius, the square root of alpha prime, which is equal to square root of 2 in our conventions where alpha prime is equal to 2. This is the self-dual radius. It's the radius that maps to itself under T-duality, the unique radius that maps to itself under T-duality. And you might think something special should happen to the bosonic theory at that radius. And we're going to see that that is indeed the case in today's lecture. And we'll see a little more as well. Okay, so let's remember our formula for PLR. This was equal to n by r plus minus omega r by alpha prime. And then setting alpha prime equals 2, this went to n by r plus minus omega r by 2. Okay, now let's set r is equal to square root alpha prime, which is square root 2 in this formula. Okay, so we get n by square root 2 plus minus omega. Now r is square root 2 divided by 2. So this is also 1 by square root 2. Okay, so we get that at this value of the radius, PLR is equal to 1 by square root 2 into n plus minus omega. Okay, the fact that the overall factor went out, that n and omega were on the same footing at this radius, is simply a restatement of the fact that this is the unique radius invariant under T-duality. Because T-duality interchanges n and r. Okay? And under this interchange, the theory remains invariant. And you see that here. These two appear on the same footing. Right? Okay. Now, let's look at the vertex operators of this theory. So the vertex operators of this theory are e to the power I P L H, and this left moving part of H, and e to the power I P R H, then multiplied by del H and various number of derivatives on H. Okay, these vertex operators become particularly interesting when we choose, on this side we choose n is equal to w is equal to plus minus 1. You see, when we do that, this vertex operator becomes, okay, I should have said actually that the vertex operator in general was e to the power I PLH HL plus PRHR. Right? It's just a package deal, it comes together. You have PL with HL and PR with HR. Okay? Now, if we choose n is equal to w is equal to plus minus 1, you see, when n and w are equal to each other, PL becomes 2 or minus 2 divided by square root 2, but PR becomes 0. So you see, now we've got a vertex operator that is purely left moving. Okay? And this vertex operator is e to the power plus minus I square root 2, I is here, square root 2 H. H, this is HL, left moving part of it. Is this clear? Okay. On the other hand, if we chose n is equal to minus w is equal to plus minus 1, then you see that the left moving part of H drops out because PLs are 0. But the right moving parts are plus minus 2 by square root 2. So we get e to the power plus minus I square root 2 HR. Okay? So two special things have happened at this special value of the radius. First, there are legal vertex operators that exist in the spectrum, that are dual to states, okay, that are single valued with respect to all other vertex operators, okay, which have become purely left moving and purely right moving. This is, of course, apart from the operators which were analytic derivatives of H, which were, of course, purely left moving. Okay? So there's a new purely left moving operator. The second thing that's special about these operators, I mean, you see when you look at the dimension, the scaling dimension of these operators. This guy has H is equal to P squared by 2. The formula for e to the power I P x, its left moving dimension is P squared by 2. It was 4 by alpha prime, alpha prime by 4 P squared. Alpha prime P squared by 4 and alpha prime is 2. Okay, so it's P squared by 2. So H is equal to 1 for both these operators. Right, because square root 2 squared by 2 is 1. Similarly, here we've got, and of course H bar is equal to 0. It's purely left moving. And we've got H bar is equal to 1 and H is equal to 0 on this side. Okay. Now, when you have operators that are purely holomorphic and have H is equal to 1, okay, it's a general fact of conformal field theory, one that we will study in detail in the second part of this course, that these operators obey an interesting chiral algebra, have an interesting chiral algebra within themselves. Okay? So I'll just tell you 2 minutes of it. We'll come back to this study in more detail at a later part of this course. But I'll just give you 2 minutes of why this is the case. Suppose you've got a bunch of operators, let's call them JA, all of which have dimension 1 and are holomorphic. Okay? Now let's consider the operator product expansion JA of Z with JB of 0. Okay? Yes.
Del H will be this kind of operator.
Exactly. Del H is also in this set. Del H and del bar H is also of that sort. Also dimension 1, also purely holomorphic. Okay. Exactly. So suppose we consider JA of Z, JB of 0. Okay? Now, here we can analyze what could appear on the right hand side of this OP very much like we did when we studied the stress tensor. Okay? The net dimension on the left hand side is 2 because each of the J's carry dimension 1. Okay? So the most singular term that could appear is like a 1 over Z square. The coefficient of 1 over Z square has to be identity because the coefficient of that operator has to be an operator of dimension 0, and in unitary theory the only operator of dimension 0 is identity. Okay? The next, if we stick to single valued things, as we should because these are genuine operators in the theory. Okay, they're single valued by themselves, not as part of a composite operator. Okay? That's really important, right? You understand that these are single valued by themselves. Okay? Like the stress tensor was. Okay, so we stick to a single valued operator product expansion of this theory. The next thing that we could get the next subleading singularity is 1 over Z. But the coefficient of that has to be some operator with dimension 1. Let's say that this is the full set. JA spans the full set of dimension 1 holomorphic operators in our theory. So you see that from what we've discussed, it should be that that this takes the form KAB by Z squared plus ABC JC of 0 divided by Z plus 1. For some as yet unknown constants, KAB and FABC. Is this clear? Just single valuedness, matching dimensions, and whatever follows after that is going to be regular. So the form of the singularity of this OP has to take this form.
Yeah, why single valuedness fixes the second term?
Single valuedness meaning there's no z to the 3 halves.
Okay, okay.
It's only integer powers of z.
No branch cuts.
No branch cuts. Is this clear? Okay. Now, something else that we have studied. See, when we have these dimension 1 operators, their expansion on the plane is given in this form. You'll have JAN z to the power n plus 1. As always, that extra plus 1 is because of the transformation. N carries is measuring the energy of the operator, the dimension of this mode. The extra plus 1 is because the extra translation from cylinder to plane because of dimension 1. Right? So, okay, now the operator J0, the guy that carries no dimension, no energy, has no h, J0 is equal to integral 1 by 2 pi I, integral JA z dz.
What is this A index?
A index is the number of possible, you can have many of these U1 currents, many of these dimension 1 holomorphic currents. A is just labeling which one. In the example we're studying now, you'll see what this A is in just 1 minute. Right now it's abstract. It's whatever it is. Is this clear? Okay, excellent. Now, these objects, J0, the dimension 0 operator, has a clear interpretation. It's the conserved charge corresponding to some symmetry. Dimension 0 object, you take a conserved current of dimension 1 and integrate it over this. In general, the conserved charge is Jz dz minus Jz bar dz bar, as we derived earlier. But in this case, the current was purely holomorphic, so there was no Jz bar. Okay? So this is the conserved charge. So let me call this J0A. Let me give it a name. Let me call it QA. Suppose I wanted to compute the commutation relations of these charges, QA commutator QB. We would do it using the contour trick, but we've done this a zillion times in this course, and we know the rule. The rule is that we will get, you find the pole, find the residue of the pole, take that residue and integrate it over a circle, and that's the charge you get on the right hand side. Okay? But the residue of the pole is in front of our eyes here. It's F, A, B, C, JC. And the integral of JC over the contour is just QC. And so therefore what we get is that this BC, QC. Okay? So you see that when we have these dimension 1 holomorphic currents, the zero modes of these currents obey an algebra that is very familiar to us. It's the algebra of a Lie algebra. Okay? So the zero modes of these currents obey the commutation relations of a Lie algebra. Okay? So we basically here are able to identify this A index. This A index is the indices labeling currents or labeling charges in Lie algebra. So the full symmetry group may be SU2 times SU plus SU3 plus SUN plus E6. Then there will be A index for all the generators of SU2, A index of all the generators of SU3 and so on. The full set of A indices have to be we're looking at unitary theory. So it has to be the set of indices of compact, finite dimensional Lie algebras. Is this clear? Does this answer your question? Okay, this is just in general. Okay, now the study of this algebra, its representation theory and its implications for conformal field theory, when it's implemented, is a very interesting. It's the study of Wess-Zumino-Witten theory, or the study of these current algebras, they're sometimes called. Okay, and this we will address in the later part of our course. Okay, there's a very large amount known about them. Very beautiful, these theories which have these, well, the minimal theories that have these symmetries are solvable. You can find all their correlation functions. And there's very beautiful connections with Chern-Simons theory. All of this we will discuss in the later part of the course. Okay, I just wanted to introduce the setting to you in 2 minutes.
What is Delitzsch was generating translation energy?
Sorry, say again?
Delitzsch was generating translation energy. What is this other operation?
Good. So first, let's look at that algebra. Okay. So far we've just said some generalities that helps put everything in context. Now let's return to our specific theory. This is called a chiral algebra. This is a particular example of a chiral algebra. It's chiral because it's function only of z. There's no z bar in it. Yes?
So the number of AAs, the A, that is there a limit on, can it be infinite? Would that also be called a chiral algebra?
Well, I suppose, would it be called a chiral algebra? I don't know. In familiar situations, it's finite.
Right, exactly.
Yeah, you would need infinite central charge to have.
If you have an infinite number of such things, will the theory that you have in the back, will that still remain a CFT? Because presumably the central charge is the infinite.
Yeah, the theory would have, sort of genuinely. Maybe you could consider it as a limit of some finite stuff. Maybe that's the way to think about it. So that's how we think of large n theories, right? We think of them at finite n and take the limit. So maybe that would be a way. I don't know, but.
These groups, do they have to be compact?
I think they have to be compact in order to give you unitary representations, to get your representation theory to be unitary. So if you want this to be a unitarily implemented in a unitary quantum field theory, in particular, this algebra has to be implemented unitarily. And that is only possible with compact. Now, of course, you can study this when it's not compact, giving up this condition of unitarity. And this is very much done. So as you know, SL2R times SL2R Wess-Zumino theory is of great use in string theory on the world sheet of the string. This is because theories on the world sheet of the string don't need to be unitary in order for space-time physics to be unitary. Okay? So you need, but if we're sticking to unitarity, of the conformal field theory itself, it needs to be unitary. Okay? The reason that the theory on the conformal field theory doesn't need to be unitary for the space-time physics to be unitary, so we only require unitarity in the BRST cohomology. That's like you need every state to be BRST equivalent to some unitary state. So the states that are not unitary are thrown away. Just like when you consider gauge theory. The A0 oscillators are naively non-unitary because they obey the condition A0, commutator A0 dagger is equal to -1 rather than +1. Right, because it falls into a multiplet of Lorentz symmetry. And yet that's not a problem because by gauge invariance, you kill the states that would come by quantizing these A0 oscillators. So there's a sophisticated version of that in string theory. Okay, that allows non-unitarity on the world sheet. But at the moment we're looking at world sheets that are, conformal field theories that are unitary in themselves. Okay, not that we're looking very much at them. I mean, we just, So you could certainly generalize this consideration to non-compact Lie algebras if you give up the requirement of unitarity.
Given the set of JA, can I make some comment about the central charge? Because the way I found central charge is by taking the ODE of T with T.
Yeah, it's an excellent question. And the answer is yes. There is this thing called the Sugawara construction. The Sugawara construction tells you how to construct a stress tensor of such theories in terms of bilinears of the currents.
We will study that.
We will study that later. We'll leave that for. These are excellent questions. It's a very rich subject. A good 1/3, I think, of the yellow book is about these theories, right? So it's something. All these we will study. It's very beautiful stuff. We will come to. But at the moment, we're looking at something much more prosaic. We're looking at one example. Okay, fine. So in this one example, as Harshal asked, let's compute the following. I've given you the general structure. Now, those of you who don't believe what else can it be arguments, like to see calculations, right? I'm one of these people. Okay, so let's do a calculation and see what happens. So let's say now, as you guys mentioned, there were 3 vertex operators, 3 dimension h equals 1, h bar equals 0 operators in this theory, which were e to the power I square root 2h, e to the power minus I square root 2h, and del h. We'll keep I del h. Okay. Let's look at the OP between pairs of them. First, let's take this guy with itself. E to the power I square root 2h of z with e to the power I square root 2h of 0. Okay. Remember mnemonic for how to calculate. We're going to get normal order product of these times some factor. Our mnemonic was take the 2-point function of this and raise the e to the power that 2-point function. That gave you the factor. Okay. Now the 2-point function of h of z with it. So what was it? H of z, h of 0. Somebody remind me, was it half? It was log of z with a minus, what was the factor behind this? Alpha prime by 2 and therefore 1. Thank you. It was minus this. Okay, so we get h with h, that comes with a minus. Okay, then I with I, that comes with another minus, so you get a plus. And you get square root 2 with square root 2. Okay, so that gives you z square times normal order. Z square. H with h. Was it alpha prime by 2? Let me get the factors right. I think it should have been z. What?
This also alpha prime by 2 r squared.
R square. What is R?
The radius of
No. I mean, here it's just 2 times whatever the factor is, right?
But that also contains 1 by r, right?
There's no R is everything is here. R was whatever square root 2, right?
I'm saying the mode of it, these vertex operators are e by r plus.
I understand, but we've set what R was, right? R was square root of 2. Okay, and once we've done all of that, we got the square root. Sorry, I'll just give me a minute to look up these. Alpha prime by 2, you're right, alpha prime by 2 log z square. Why am I messing up then? So there was alpha prime by 2. Oh, I am not messing up. Square root 2 into square root 2 into half. Sorry. So to the power 1. Right, because of the by 2. No, but alpha prime was 2. Yeah. It's a bit odd. No, it's correct. We wanted z square. Sorry. Z square is correct. I square root 2h of z minus square root 2h of 0 plus. Yeah. Okay. At this stage, all we care about is that it's regular. Okay. So this contributes neither to KAB nor to FABC. Okay. But now let's look at this guy. Let's look at e to the power I square root 2h of z, e to the power minus I square root 2h of 0. This guy, by the same calculation, is 1 by z squared times normal order e to the power I square root 2h of z minus h of 0. Clear? And now let's Taylor expand this h of z. So this h of z is h of 0 plus z del z h. Bring it down to first order. So we get, so 1 by z squared into 1 by z squared into 1 plus square root 2 del I square root 2 del h. Z, thank you. 1 by, so let's 1 plus I square root 2 by z. Is this good? Excellent. So we've got a non-trivial correlator here. Now let's do the same with I del h of z with e to the power I square root 2 h of z. Okay, this we actually have already worked out while studying general conformal field theories, because this is the generator, this is the current, OP of a current with an operator that carries charge under the current. The charge under this current was square root 2. Okay. So you know already that we're going to get a pole times the operator that we started with times the charge, which is square root 2. Okay, let's just check it anyway. Okay, so so let's write this as I del h times sum over n I square root 2 h h of 0 to the power n divided by n factorial. Okay. Now we get the 2-point function. That 2-point function, you know, there are n choices for what to contract with, so it makes n factorial n minus 1 factorial. We pull out an I square root 2 from that. Okay, and we get a factor of alpha prime by 2, so log z, and then a derivative of that. So that's 1 over z. So this goes to minus square root 2 e to the power I h of 0 by z. No minus sign. Why not? Puts up a minus sign, plus. Thank you. Thank you. No minus sign. Excellent. Okay. And finally, let's look at clearly with the other guy, I del h e to the power minus I square root 2 h of 0 goes to minus square root 2 e to the power minus I h of 0 by z plus. Clearly that's the same calculation. Okay. And of course, we know that I del h of z with I del h of 0 gives, let's see, we get I is minus 1, then h gives a minus, so that's 2 minuses. Then we differentiate once on this guy, so that gives us a plus 1 over z, and then we differentiate on the other side, so there are 2 minus signs, so there are no minus signs. Okay, so we get totally 1 by z square. Okay, is this clear? So now let me use some suggestive notation. Let me go to the next board. Let me use some suggestive notation.
What was the reason you were giving current to e to the power I root h? Like before doing the calculation you were doing.
Yeah, I'm saying I del h was the current corresponding to translations. What is the charge for translations? It's momentum. But those operators have momentum square root 2 because they e to the power I square root 2h. So we know that the charge should have been the momentum, which was square root. The OP of a current with a charged operator, the commutator of a current of charge with a charged operator is the charge. Okay? So that should be the pole in the OP.
But shouldn't there be also some 1 by z square also?
Why?
Because 1 by z captures the pole, right?
Yes.
But that does not necessarily eliminate the 1 by z.
Ah, you're saying how do you know that there was no 1 by z square? Yeah, that could have been. In this case, it's not. Now, I knew that there was not for a reason that's going to become clear in a minute. Okay, the reason is that I know that we're dealing with SU2. Okay, so look, let me call I del H, let me call this JZ. I may be getting my normalizations wrong. We may have to renormalize in a little while, but let me start with this. I del H is equal to JZ, and let me call e to the power I square root 2. I always mean normal ordered. I don't always write that, but I always. Let me call this J plus, and normal ordered e to the power minus I square root 2h of Z. This is J minus. Okay? Now, with this notation, we see that the OPs we've worked out are Jz of Z, Jz of 0 is equal to 1 by Z square. Okay, we've also worked out J plus of Z, J minus of 0, that was there. I'm writing only the non-trivial ones. So this one is equal to 1 by Z square plus I square root 2 Jz of 0 by Z. You need to keep your wits about you to distinguish 2 from Z. Okay. Okay. Should be no I, maybe you're right. We didn't get an I here? But what about in this Taylor expansion? We got this I from the Taylor expansion.
Yes.
So we just to first order in Taylor expansion. So there is an I, right?
No, but in the definition of ZZ.
Ah, thank you. In the definition of JZ, yes. Thank you. JZ. Up and down is the same thing. Okay. What about J minus of 0, J plus of Z? Well, this of course we can work out just by switching, by translation, right? All it will do is switch Z to minus Z. You can see that, right? Because we now center to J minus of Z, Jz plus of 0. All this does is center to, make this the origin, and then this becomes minus. Okay, so we'll get minus of what we got. So we will get is equal to 1 by Z squared minus square root 2 Jz of 0 by Z. Okay, and we had Jz of Z, J plus minus of 0 was like, where was that? That was here, plus minus square root 2 J plus minus of 0 by Z. Okay, so we see two things. First, we see that all these 1 by Z square terms were the same. Okay, and second, we see that what we've got here is very similar to the commutation relations of the SU2 algebra. Right? The commutator of Jz with Jz is 0. The commutator of Jz with J plus is J plus. Commutator of Jz with J minus is minus J minus. And the commutator of J plus with J minus is Jz. Now, I will leave to you, you will have to figure out, we need to figure out with what normalization in terms of jx and jy, we'll get these factors of square root 2. I'll leave that to you to check. I'm not going to try to do that here. Notice also here that this 1 is the invariant form on SU2. Right? It's the form that clicks jx with jx, jy with jy, jz with jz, and everything else is 0. So that means it clicks j plus with j minus with j plus, jz with j plus, jz, and everything else is 0. Okay? So if we work, I'm not going to try to dare to get the normalizations right here for you. But up to some factors of 2, if we define jx as j plus j minus by 2, and jy by jx, j plus minus j minus by 2 times I, with the right factors of 2, this will turn into ja of z, jb of z of 0 is equal to delta ab by z square plus fabc, epsilon abc, maybe, yeah, plus epsilon abc jc of 0 divided by z, where this epsilon is the is the structure constant for the SU2 algebra. Okay? So I'm going to ask you, maybe there's an I here. Hey, you'll have to look at that. Okay? So you see that what we've got in this situation is the current algebra for SU2. Is this clear? So we had this general theory saying that if we've got these conserved currents, these H equals 1, H bar equals 0 currents, their algebra must make up, must include singularities that have Lie algebra computation relations. And we've identified the Lie algebra in the situation. It's SU2. In fact, the general theory tells us, and it's not very hard to see, that what appears here is always the invariant form, the killing form of if you've got just one single Lie algebra. What appears here is killing form by z square, and then in some normalization, some integer. We will study all this as we go. That integer is called the level of this current algebra. Okay? And then what appears here is always, of course, the structure constants. What we are encountering here is SU2, is the SU2 current algebra at level 1. Okay? What that means you probably don't know now. We will discover. Okay? All that I really wanted to, this was a little diversion, I wanted to show you that the free boson at the self-dual radius implements the SU2 current algebra at level 1.
What is level means? Like, are they linked to do with winding sector?
No. Level, unitarity forces this form to be some number times that, forces an integer. That integer is called the level. Nothing to do, obviously, with winding. There are many things to say about the level, but let's leave it.
So these J plus and J minus, they just reduce and they either increase or reduce the momentum of a given state.
They increase, yes. They add momentum or reduce momentum from the state within this discrete amount of square root 2.
So, but this representation is in some sense infinite dimensional because the momentum can be infinite. Absolutely. The representation is infinite dimensional, not though for the, you see, this algebra closes on itself, right? J plus with J minus gives you 0 and so on. But it's certainly true that the full current algebra is infinite dimensional. Okay? So the full current algebra allows you to act with the non-zero modes of J. Not just J0, which we've been looking at for now, but the non-zero modes, and that allows you to act with as many of these J's as you like. Here in the zero mode sector, since we've got the SU2 algebra, from unitarity we know that the representations are finite dimensional. Okay? And you might ask, how does that work? You could have asked this in SU2 representation. And the way it works is that if you start with the highest weight states,
state and act 2j plus 1 times with that, with the lowering operator, it looks like you will get states with increasingly low jz. Momentum is jz, but it gets annihilated. That's what's going to happen here. Okay? So, though it naively seems that even in the zero mode sector, you should have got states with arbitrarily high or arbitrarily low momentum, that does not happen for the usual SU2 or finitely algebra reasons. However, that does not apply when you have non-zero modes. When you look at the j's, we expanded in there right at the top of the board, ja is jan by z to the pi n plus 1. If you look at the modes not with n equals 0, with higher n, there's no reason for those guys to need to be finite dimensional. In general, they're not. Of course they're not. Okay? But just in the zero mode sector, despite appearances, it's finite dimensional for the usual re-algebra ways. Okay, excellent question. Other questions or comments? Okay, fine. Now, so what have we discovered? You see, if we take circle compactifications at general radius, at every value of the radius, there is a current algebra generated by del H and the antiholomorphic by del bar H. Okay? And that current algebra just corresponds to translations. Right? The fact that the free boson has translation symmetry, that we knew. This current algebra exists. What we've discovered is that at this particular value of the radius, in addition to translations, there are two other new symmetries, okay, which enhance the symmetry group from U1, which is what it is at a general point, to SU2. Okay? Just a quick comment about string theory. In string theory, these currents that you see here turn into gauge fields in spacetime. Okay? So in string theory, these U1 currents map to the fact that in spacetime you have a U1 gauge symmetry. And that U1 gauge symmetry comes about by Kaluza, basically from Kaluza-Klein. Actually, there's left moving and right moving part coming from B mu nu and H mu nu. So Kaluza-Klein gauge field is the B mu nu reduction on the circle. But okay, these are just simple effective field theory things in gravity. At this special value of the radius, this SU2 tells us that you have an SU2 gauge invariance in our theory. This SU2 gauge invariance, from point of view of low energy effective field theory, is a miracle. There is no geometrical isometry. There are no geometrical isometries that give you SU2. Normally from compactification, we get gauge symmetry because of isometries of the compactification manifold. Okay, there's no geometrical isometry that gives you this SU2, and yet it appears in the theory. You see, it's an SU2 that involves mixing of momentum modes and winding modes, because the modes that created that had n is equal to w is equal to 1. Winding modes are not seen in the low energy effective field theory, so it's an extremely stringy thing. Okay? Both from the point of view of conformal field theory and from the point of view of string theory, the emergence of this new symmetry at this point is quite interesting. Okay, fine. Now, that's all I wanted to say about the circuit compactification at this self-dual radius. Basically, what we've seen is that the theory has a new symmetry, namely this SU2 symmetry. We will come back to this at the end of the lecture when we tie it up with the study of orbifolds. But any questions or comments before we proceed?
What about higher order currents? Do they not follow this SU?
What do you mean higher order currents?
Like z to the power n plus 1, z0.
Okay. The Jn's for n not equal to 0?
N not equal to minus, n not equal to 0.
N not equal to 0, right. So, there is an algebra of the higher order current. Okay? And that algebra, I'll write it down for you, is J A N J B M is equal to delta n comma m delta AB k by z square. Oh, not by z square. The modes plus FABC JCM plus n. Roughly speaking, this is the algebra. I may have got some I and so on wrong. K is the level of the current algebra. Okay, you see that they form an algebra, but it's an infinite dimensional algebra. Because if you take J1 with J2, you get J3. You take J3 with J2, you get J5, and so on. It never ends. Okay, this infinite dimensional algebra is called the Cauchy-Moody algebra. Okay, and the representation theory of this is very interesting. Okay, but we will return to this at a later part of the course. Was that your question?
Yes, but what, like, it can be finite dimensional if these structure constraints are at some stage?
No, it's never finite dimensional. Because you see, the finite dimension is not coming from the FABC. It's coming from the MNs.
No, but if for some C, FABs, it's 0, let's say.
The only, what you need is that all FABs are 0. Otherwise, you'll keep being able to build up. Yeah, F sub to satisfy Jacobi basically have to be the structure constants of a Lie algebra.
Yeah, then if you have this thing that he's talking about, F will identically go to 0. You can't have a gradation.
So what Karthik is saying is that the only way you're going to get this, basically in the U1 theory, it will happen. Right? Because all F's are 0 then. Okay? But there's no other place where it will happen. Because we know all the FABCs for Lie algebras. Right? It will never happen. Yeah. Okay. Excellent. Other questions or comments? Excellent. So, far we have studied this moduli space of circle compactifications. I'm working in units of alpha prime equals 2. So we had this, the self dual radius, square root 2. This is an SU2 theorem. Then we had the thing, we called it radius 1 in our discussion, but that's same as radius 2 by T duality. For the purpose of this diagram, I'm going to write 2. Square root 2 times this rather than square root 2, this by square root 2. Okay? Here we had bosonization. The theory here was the same as the theory of two free fermions. Okay. There's something interesting that also happens at 2 times square root 2. There's something interesting that also happens at the radius 2 times square root 2. And that is what we're going to head towards understanding now. Okay? Excellent.
In our whole calculation for this SU2 algebra, we took n equal to 1, w equal to 1.
Yes.
We could have taken n equal to w as well.
N is equal to?
For the number of this momentous
Yes.
and winding, we could
Yes.
have taken n equal to w as well.
We-
Not just one.
N equals 2, w equals 2, for instance. You could have, but then you're not going to get it's true that you get a chiral operator, but it's not a chiral dimension 1 operator.
Yeah.
Okay? Now you can ask what interesting thing happens there. Yeah, something probably very interesting does happen. It's a good question. Of course. So let's suppose that we take n is, let's explore that for a minute. So suppose we take n is equal to w is equal to, let's say, some m. Okay? Our dimension of operator is going to be m square. Yeah, the holomorphic operator will have dimension m square. Okay. Now, okay. So what you are interested in is looking at the algebra formed by this full set of chiral operators. Yeah, it will be some very complicated algebra. Okay, it will be some very complicated algebra, and maybe somebody knows, maybe it's some W something, W infinity something. I'm not even sure. But yeah, it will be some very complicated, perhaps interesting chiral algebra. I don't know what to say about it. It will exist. Usually free theories have huge, especially in this case. In this case, it probably has a huge chiral algebra. Only one subalgebra of that is the Westermino-Witten. Yeah. What? If I knew what a W algebra was, I might be talking about it. You know? Yeah. You know, there are these larger algebras.
W algebras you have J's which have spin 2, 3, 4.
Spin 2, 3, 4, 5. Good. So we have here spins m squared for all m. Is that a square W algebra? I have no clue. Some. It's some.
They're hard to manage even if you just have one spin 2, 3
Yeah. So here we have spins 1, 4, 9, and so on. That's our algebra. You can work out anything you want about it. Because the OP here, it's in your hands, right? You work it out. Now, whether somebody has studied this and said something about it, I don't know. Okay. Excellent. But excellent questions. Okay. So now we're heading towards studying this point. And the route to studying this point turns out to be a sort of surprising one, not an obvious thing. It's not like the way you make progress is staring at this point. It's by doing something else. Okay? And that something else is to study what are called orbifolds. Okay. So let's say that we look at our Lagrangian, our free boson Lagrangian 1 over 8 pi because we set alpha prime to 2. Del alpha x, del alpha x. Okay? We take that action and we look at it. And now we imagine that x for a moment is not compact. Is compact, is non-compact, yes. Has no circle identification. Yes, we will change that in a bit, but imagine that at the moment that it has no circle identification. Now, let us, you see, this action has a symmetry. So the symmetry under x goes to minus x. The symmetry is obvious because the action is bilinear in x. Okay? Now, oftentimes when you have a symmetry in a theory, you can gauge the symmetry. Now, the kinds of symmetries we're used to gauging when we study four-dimensional physics, when we study QED, is gauging continuous symmetries. And that gauging process forces us to introduce gauge fields. Okay? On the other hand, when you have discrete symmetries, if you try to gauge that symmetry, first, what is the process of gauging? Gauging just means if you have two configurations that are related by that symmetry transformations, you identify them. That's what gauging means. And if we wanted to, the program of making gauge theories in, let's say, 4 dimensions is one of trying to take a global symmetry and try to make it local. And then when we do that, we need to introduce gauge fields. Right now, we're going to do something much less ambitious. We're not going to try to take a global symmetry and make it local. Just trying to take the global symmetry itself and try to study a theory where a configuration and its symmetry mapped counterpart are identified. Okay? So, if you have a shape x of sigma t, and you've got another shape minus x of sigma t, which is going to declare that these two are the same physical configurations. That is our game. Okay? That is, of course, part of gauging, but a very simple part of gauging. Doesn't require the introduction of gauge fields. Okay? So this is what we're going to try to do with this symmetry. We're going to try to take the symmetry, which is x goes to minus x, and promote it to an redundancy. Okay? So that configurations that are related by the symmetry are going to be identified as the same physical configuration. Is this clear? Is what we're trying to do clear? Okay.
Was this the original motivation to study these orbitals?
No. I don't even know. Yeah. This is just a narrative for the class. Okay. 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 So let's see. Suppose I had this this symmetry. This, by the way, this gauging is very similar to compactifying X. Because when we compactified X, when we took X and said that it was actually lived on a circle, we just declared that X and X plus 2 pi r are the same point. Right? That was what it meant by compactifying X. Okay? So in that case, we gauged with a discrete translation. The translations of all magnitudes were a symmetry of our theory. And we gauged the theory with a discrete translation. That was the compactification. Now we're going to try to gauge the theory with the reflection. X goes to minus X. Is this clear?
This compactification X identified with X plus 2 pi r and X and minus X, they can't go hand in hand.
They can. In fact, that's what we'll do next. We will do both together.
But how, like...
Hang on, 10 minutes. Yeah, well, that's what we'll come to as soon as we finish this discussion. Okay? In fact, the reason that orbifolds were, I don't know if this is the reason they were invented, but the reason they became so popular in string theory is people trying to make compactification. You know, these conformal field theories in string theory represent internal manifolds. Right? Because the world sheet of the string is a conformal field theory with C hat equals 15. And what you want is 4 dimensions, I mean for many purposes, what you want is 4 flat dimensions times something else. So that something else, the C hat equals 6 internal manifold, is some other conformal field theory. People wanted to make more and more conformal field theories that they could work with, that broke all kinds of symmetries, but needed to be compact. So for phenomenological purposes in string theory, you need orbifolds on something like a circle. And we will come to that. Okay. Okay, excellent. But let's keep going. So we have this X goes to minus X. So let's see. So suppose we've got our cylinder where we're studying our theory. Okay. Now, just like when we studied circle compactification. Okay. Just like when we studied circle compactification, we have now our Hilbert space, in fact even classical phase space, splits up into disconnected sectors. When we studied the circle, the sectors were labeled by winding. It was because sigma was compact. And as you went from sigma to sigma plus 2 pi, you had to come back to the same configuration. But the same configuration didn't mean the same X. In the circle case, it meant X plus 2 pi r times n, because 2 pi r times n times X was the same physical configuration as X. Okay? Now, our identification is in some sense simpler. We have X goes to minus X. Okay? So you have two sectors. One is which, when you go round on the sigma circle, X comes back to X. The second is when you go around the sigma circle, sigma goes to sigma plus 2 pi, X goes to minus X. Okay? The first is the untwisted sector, and the second is the twisted sector. Is that clear? Okay? Now, in the untwisted sector, the theory is exactly the same as the non-compact, the unorbifolded non-compact thing, except for one constraint. All states in the theory have to be invariant under the operation of doing X to minus X. Right? Because we've declared that, when we study gauge theory, the only states in the theory are gauge invariant states. Gauge invariant states are states that are left invariant, go back to themselves when we act with all gauge transformations. But the gauge transformations here are just 1 plus the operator that takes X to minus X divided by 2. Is this clear? So all states have to be even under x goes to minus x. Under the gauge transformation that implements x goes to minus x on, the Schrodinger function. Is this clear? Okay. So let's see. How does that work? Okay. You see, x goes to minus x. Okay, x goes to minus x. The states that are invariant under this are those that built out of an even number of oscillators and have zero momentum. E to the pi ipx is not invariant under x goes to minus x for any p except 0. And oscillators are some number of derivatives on x. If you have an even number of some number of derivatives on x and some number of derivatives on x, even number of those guys, the derivatives don't matter, even number of the oscillators themselves. Okay? Alpha minus, okay, so let me say this more clearly. You remember, right, that the full spectrum of the non-compact free boson was generated by alpha minus n to the power nn, product over n, any number of oscillator states for the nth oscillator times e to the power ipx, so times p. So acting on the momentum p vacuum, this was the general state. Now p must be 0 because p is taken to minus p. And symmetry. So the states in the untwisted sectors are those with p equals 0, and each of these alphas goes to minus itself. Each of these alphas goes to minus itself under x goes to minus x, because alphas were the Fourier coefficients in the expansion of x. Or in operator language, alpha n was del n of x. X goes to minus x, it goes to minus itself. Is this clear? Okay, so the states in the untwisted sector are precisely those states in the free boson, non-compact free boson, that have momentum equals 0. Okay, that have momentum equal to 0 and that have an even number of oscillator excitations. Okay, in 2 minutes we'll compute the partition function of these things.
So does the role of creation and annihilation operator change under x going to minus?
No. Creation and annihilation operators is the creation annihilation operators goes like this, right? So suppose we have x of sigma and tau. Okay, we have let's look at the left moving sector. So let's say x of z. We have e to the power I n sigma, let's say plus tau alpha n plus e to the power I n sigma minus tau, sorry, minus sigma minus tau, minus sigma plus tau, alpha n dagger. I may be getting which is alpha n and which is alpha n dagger the other way around. Let's go. I think so this should be alpha n and this should be alpha minus n. Okay, now under x goes to minus x, alpha n goes to minus itself and alpha minus n goes to minus itself. Commutation relations remain unchanged because both pick up a minus n. Just a phase, right? Okay? Alpha n is defined by whether it multiplies a positive energy thing or a negative energy thing. Multiplying by a minus sign doesn't change that. Is this clear? Okay, excellent. A linear combination of? If you take a linear combination of p and minus. Okay, excellent. Yes. Oh, you're right actually. You're right. I said it wrong. You're right that you're absolutely right. I said it wrong about the zero mode sector. What is true is Harshal said it right. It's not only the zero momentum sector that survives. It's all things that are even under. Thank you, Harshal. Okay, so let me say it correctly. As Harshal explained, the full untwisted sector is actually a sum of two things. You can have cos p, so p plus minus p. We could have, thank you, p plus minus p, and then times even. And you can also, sorry, I said that wrong, that was a bad miss. Okay, you're absolutely right. You could also have odd times p minus minus p. That is actually the full untwisted sector. Sorry about that. P equals 0 is just one state in this. You could have just much larger sector. Sorry about that. That's absolutely right. Yeah, this is the full untwisted sector. Thank you. Okay, there is a calculation for which only P equals 0 contributes. That's in the twisted partition function, which is why I was getting mixed up. That will come in a minute. But thank you, you're absolutely right. Okay, that's the full untwisted sector. Thank you. Okay. Okay, so this is the spectrum in the untwisted sector. Then, of course, we have the twisted sector. Okay, so now in the twisted sector, our expansion has to, when we go from sigma to sigma plus 2 pi, x has to go to minus x. So instead of n being integer, n is now half integer. Is this clear? So our expansion will be, let me write it in operator language. Okay, del x will be equal to sum over n alpha n divided by z to the power n plus 1, where now n is half integer. This is an operator language on the plane. Of course, on the cylinder, it's just that these alpha n's, all those n modes are half integer. Is this clear? Okay. In particular, there is no n equals 0 there. So there are no 0 modes. Okay. Now, this is of course very intuitive. There, in the twisted, you see, we've got this x space and we've got a fixed point, namely x equals 0, which is the point that is left invariant as you take x to minus x. Okay? A string that obeys the boundary condition, x of 0 and x of 2 pi are identified up to minus, is doing this. A normal string does this. Comes back to itself as you go down to pi. Okay? Here the string is doing this. Now, because of this, the string is tied to this point because its center of mass, so to speak, is at the origin. So it can't move around. So there's no 0 mode. Is this clear? No. Sorry. Okay. What was the boundary condition in the untwisted sector? The boundary condition in the untwisted sector is x of 2 pi is equal to minus x of 0. Is this clear? Okay. So this is x of 0, the beginning of the string. This is x of 2 pi. It's the end of the string. The string is going from here to minus its beginning point and end point are related by minus sign. So because of that, the string always has to stick around the origin. No matter how far this beginning point was, the end point would have to be equally far on the other side. It can't all move far away. Is that clear? Okay. So the string therefore the string has no 0 mode motion. Okay. What it does do is vibrate as it stands around that point. And these are the alpha minus half, alpha minus 3 halves, and so on oscillators.
It will not move in a space.
It will not overall move. It does all kinds of things, but there's no center of mass motion.
There's nothing to do with boundary conditions, like they are free.
The boundary, yeah, it's just whatever's happening there has to happen here. Yes, it can. Okay.
So that's why I was saying that you can't have again x goes to x plus 2 pi.
Hang on. We'll talk about x goes to x plus 2 pi. Okay. What you will have is when you have x goes to x plus 2 pi, you have 2 fixed points. Just hang on for a minute. We'll come to that. Okay. Okay, thank you, Harsha. Okay, excellent. So so this is our untwisted sector. Now, sorry, this is our twisted sector.
This is for closed string.
This is for everything is for closed strings. We've not talked about open strings so far. No boundaries in our conformity. Okay. Okay. Now there is one thing that we need to do, which is this. I told you what the spectrum was in the twisted sector. Sorry, in the untwisted sector. The sector where you didn't have funny boundary conditions. That is fine. Okay? But there is this, the question that arises is, what is the spectrum in the twisted sector? So I've more or less given you the answer to that, except that we haven't correctly yet done one thing. We haven't found the 0-point energy. Okay? You remember that in the untwisted sector, just for a free string moving around, we found the 0-point energy by adding up the 0-point energies of all the harmonic oscillators. So we found it as 1 plus 2 plus 3 plus 4 up to infinity. Okay? Here we have to do a different sum, because now we have to do the sum. What is it? One by 2, because h bar omega by 2, into half plus 3 halves plus 5 halves, and so on, because the oscillator frequencies are half, 3 half, 5 half, and so on. Is this clear? But in the last lecture we did this sum. We did this sum when computing the ground state energy for fermions in the Neveu-Schwarz sector. Okay? And let us back calculate to recover that answer. I don't remember the answer, but I remember what it had to match. Right? What it had to match was this, that the fermions in the harmonic the ground state energy of the NS sector, ground state energy of the NS sector plus what you get by the Schwarzschild shift. Okay, plus what you get by the Schwarzschild shift should give you the dimension of the lowest operator in the NS sector, which was the identity. Okay, and remember how we did that calculation? We checked that the ground state energy in the NS sector, which was in that case, because it was fermions, it was minus and minus, let's do it in the doubled theory. So it was, yeah, exactly, C by 24. So we did minus half. The way we did it last time had 2, because there were 2 fermions, into 1 by 2 plus 3 by 2 blah blah blah, that plus C, which was 1, by 24. So 1 by 24 was equal to 0, because that was the dimension of the primary, of the identity operator. Okay? And therefore we concluded that half plus 3 by 2 plus blah blah was equal to 1 by 24. Okay? So we're not going to do the same, I mean, it's the same calculation. We've got that, yeah? So this quantity therefore is equal to 1 by 48, because half of that 1 by 24. Okay? Excellent. So this now tells us what the dimension of the lowest operator in the twisted sector is. Okay? By the state operator map, for every twisted sector state, there is an operator. And the vacuum in the twisted sector corresponds to some operator. Okay, we've just computed the energy of the vacuum. We have 1 by 24, 1 by 48, okay, and then we're supposed to, in order to get the dimension, we're supposed to subtract C by 24. Oh, sorry, we're supposed to add C by 24, right? We're going to plus 1 by 24. Right, and last time we got minus 1 by 24 plus 1 by 24. Yeah, so this should be right, I hope. 1 by 24, so that's 3 by 48. Is this correct? Let me check. It's looking like an odd figure. 1 by 16, 1 by 16. Ah, that looks better. That sounds more familiar somehow. Yeah. Okay, thank you. That sounds right, but let me just check this. Ah, 1 by 16, great. So we got this right, yeah. Okay, thank you. Okay, excellent. Now,
Why we are seeing this change in zero mode energy?
why are we seeing this? Because how do we get the zero mode energy? We got it by adding up the energies, the 0-point energies of all the harmonic oscillators. But the harmonic oscillators' frequencies have changed. Okay, so just for that reason. Clear? Okay, so we had to do a different sum. It's exactly the same thing we had to do in the NS sector of the fermions. Excellent, 1 by 16 is the right answer. So thank you, Aryavan. Okay. Excellent. Now, there is one thing that in studying these orbifold theories, I'm not in this lecture going to do, but if somebody is interested, we could have a lecture on this, which is how to construct the operators, or more precisely, how to construct the correlation functions of the operators of the twisted sectors. When we studied circle compactification, the twisted sector operators were very simple. They were e to the power I PL XL plus e to the power I PR XR. We knew how to, we knew just by Wick contractions how to get the correlation functions. So there's one subtlety, the DDF operators. Nobody's asked me about it and I haven't told you. There's something about signs there that I haven't told you about. Maybe if we have the special lecture on the orbifolds, I'll tell you about that as well. Okay, but it was basically very simple. Then we encountered another such question when we started studying fermions. Right, when we started studying fermions, we looked at the operators in the NS sector and they were really very simple. They were the fermions and their derivatives. Then we looked at the operators in the R sector and there were these strange operators which had square root branch cut singularities with familiar operators. And if we just had the fermionic description, we would have just stared at that and done what I'm going to do, what I'm going to tell you about we can do with the orbifolds. But we had the bosonized description. And in the bosonized description, those operators were very simple and we could deal with them. Okay? In the study of orbifolds, there is no analog. The twisted sector operators, there is no known simple construction of these operators that will allow you to calculate their correlation functions using Wick contractions. Okay? Nonetheless, one can compute all correlation functions. All correlation functions are determined by general properties, determined by holomorphicity and singularities. And in fact, the original papers that computed, let's say, 4-point functions of these twist operators did it using this method. Okay? So this is an example of a place where we're leaving familiar terrain. In the best situation, we like to think of operators as explicit insertions in the path integrals, preferably of the fields that appear in the path integral. Okay, that's what the psi things, or e to the pi kx were like. Okay. Now already, when we looked at the Raman sector, there was no explicit operator in terms of the fermions for the operators dual to the states in the Raman sector. But we managed to sidestep this by bosonization, where the bosonic description had explicit expressions. Now we've come to a place where there's no known simple description like this, but we know what the operator must do. The operator is something that changes the sign of x as you go around the operator. Okay, we know that it does this, and we know that it has certain properties, and that itself plus this holomorphicity is enough to compute all correlation functions of these operators. So depending on interest, we could have one lecture, maybe the next one, on computations using this method. Okay, just to convince you that it's not like there's something we don't know. It's just a pain. It's not as easy. It's not Wick contractions. But you can do everything you want. Okay, but for now, let's move on. We're not going to try to understand these operators beyond understanding the scaling dimensions. Scaling dimensions, of course, we understand. We've just computed the ground state, and the scaling dimensions of the other states are now additive, right? From the oscillator expression, we have them. So the guy which is alpha minus half on this is 116 plus half. H is 116 plus half. That's clear? Okay, excellent. We can compute it using path integrals, but in the path, you can in some sense, you can. Because what you're doing is that in the path integral you're putting, let's say you want the ground state of this. What you would do is to put the condition that all x's as they go around your operator goes to minus x. But this is not enough, because this just tells you that you've inserted an operator in the twisted sector. You have to also be able to tell it which operator in the twisted sector. Okay, so there's some detail of what's happening as you go around. So you can, basically by state operator map, right? You take this, make it a tube, and insert the state of interest. You can do it, but you have to work hard. Is this clear? It's an excellent question.
You are talking about operators which are something different from these oscillators applied, or?
No, oscillators, but in the twisted sector.
But that you can, you know weights, right?
You know the weights.
That is enough here.
You see, what you can do is to compute, basically what we will do in next class, or if you guys are interested, is compute for, let's say, a ground state guy, the ground state twisted operator. Now, most of the remaining guys are obtained as descendants of this fellow. Okay, so you see there's this Virasoro representation theory, and there are primaries. In the twisted sector, there are no zero. Let's remember that for the free boson, the primaries were del x and e to the pi kx. In this case, there's no e to the pi kx. Okay, so basically, there's essentially one or maybe two primaries in this sector. So if you've got one, you've got them all, maybe two. Okay, so using symmetry, you can quite easily do these computations. Okay, if you wanted to, but I think Shreyansh, right? Shreyansh's question was, forget fancy techniques. Just instruct the path integral what you are doing. Okay, and then get the answer. The way you would do that is the following. You've got this path integral, and then you've got an operator insertion. Now, you take that and change the Weil factor so that where you put that operator becomes a long cylinder. And then you put that at this point, you have the state of interest. Now you can go and put that back. That is telling you not just that x goes to minus x as you go around, but that as you go around, you wind around n plus 1 times. Do you understand what I'm saying? For your x field. You see, what is the x field doing in the state with momentum n plus 1. As you go around, it's winding around n plus 1 times. Okay, so that's what you have to instruct the path integral. Okay, if you want to say not just that you are in the twisted sector, but which twisted sector operator. Okay, and all this can be done. All this can be done, but it's not as easy as doing Wick contractions. Okay, right. But this is an issue we leave to whenever, if we want to get into it. This is a technical job, the one that we shouldn't shy away from since we're technical people, right? But okay. In this thing, I think probably in this case just one actually. Yeah, even del x will be projected out because x goes to minus x, it doesn't survive under. Okay, so it will just be the ground state of the Ramond sector. I mean of the twisted sector, whatever it is. I think in this case there is just one prime. Okay, I would have to confirm that. But I think so. You see, the reason that you needed, ignoring zero modes, the reason that you needed identity and del x for a non-compact free boson is that T was bilinear in x's. So you could never change odd or even number of oscillators by action of L's. Okay? But as we have seen in this situation, okay, you're only allowed to put even or odd oscillators depending on whether P is minus P. And now there's not even a P because we're in twisted sector. So you're only allowed to put even oscillators. So that feels like it should be possible to generate completely from ground state by Virasoro. So I think it should be, I think there's one prime. I think there's one prime. The twisted sector. Okay, excellent. But again, this we're not going to get into at the moment. Okay, I'm going to take like 10 minutes extra today, just to complete our discussion of orbitals. Okay, the one thing that we, okay, so let's first write down a formula. Yeah, please go.
So in the twisted sector also the states are when you just again you have to apply even number.
Or even number. Because apart from twisting, you still have to project onto gauge invariant states. That is always true. Twisting is just what happens in X. In time, we have to project onto gauge invariant states. Okay? In fact, this comes directly to what Chintan was asking now. Let's take this simple orbifold theory, this simple non-compact orbifold. We come to the compact orbifold in 5 minutes. Okay? Let's look at the simple non-compact orbifold theory and compute its partition function, its torus partition function. Okay, so we have contribution from the twisted sector and contribution from the untwisted sector and contribution from the twisted sector. Let's first look at the untwisted sector. The untwisted sector was a trace of 1 plus, I'm going to call it P, the operator that takes x to minus x, parity. Okay, 1 plus P by 2. Oh. Q to the pi L 0. Are you, sorry. Do you have the class now?
No, we have a talk at 4 o'clock.
4 o'clock. Can you give me like 3-4 minutes?
Yeah, that's fine. We'll set up. Yeah.
Okay, sorry. We'll have to be quick. Yeah. Okay. So what we're doing is calculating this object in the twisted, in the untwisted. In the twisted sector. Sorry, say again? 1 plus P by 2 is the projector onto gauge invariant states. Okay? Now let's write down formulas for it. So this was Chintan's question. Is there a 1 plus P by 2 also in the twisted sector? And of course there is. Okay? So now let's take this and write down a formula for this partition function. First, the first term, which is just this, is half times the partition function of a free boson, plain free boson. So whatever it is, the thing we wrote down way at the beginning of this course, right? Anyway, I'm not writing it down, but we could write it down in 2 minutes if you want. What about this guy? This guy is the partition function with a factor of p in the trace. Okay? Now you remember how p acts. P acts by taking, p is the operator that implements x goes to minus x. So in particular in momentum it takes p to minus p. So here only p equals 0 contributes. Okay, so this is why I was mixing up. Yeah, so here only p equals 0 contributes. Moreover, what does it do for the oscillators? Okay, what does it do for the oscillators? Well, for the oscillators, it takes states with an even number of oscillator action and multiplies them by +1, but states with an odd number of oscillators and multiplies them by -1, because each oscillator has one factor of x and it implements x goes to minus x. Is this clear? Okay, so effectively it is it's the partition function in the oscillator sector with an extra factor of -1 to the power number of oscillator excitations. Okay, but that's very easily computed. Okay, it's just plus 1 over a product of n. Now ordinarily for the oscillators we had 1 minus q to the power n, 1 minus q bar to the power n. We just, exactly, minus changes to plus, so that every time you have an oscillator contributes with the wrong sign. Okay, and of course we have the 0 point contribution, the 0 point energy contribution as before. So that is whatever it is, q to the power L0, and L0 was minus 1 by 24. And then q bar to the power. This is what we have in the untwisted sector. The Z free was the same thing, but with these pluses being minuses. But 0 mode, the 1 plus 2 plus 3 plus 4. No, 0 mode, there's no 0 mode. Because it's, because we're restricting to p equals 0. Okay, yeah, so this was the same thing except that this was minus, these factors were the same, and plus there was a 0 mode contribution. The 1 by square root tau, whatever, the imaginary part of tau. I'm not trying to get that straight. Okay, so this was the partition function in the untwisted. What about the partition function in the twisted sector? Well, in the twisted sector, it's really easy. In the twisted sector, we found the 0 point energy was 1 by 48. So we had q to the power 1 by 48, q bar to the power 1 by 48. And then once again we've got this half because we have 1 plus p by 2. Okay. Now the 1 is just what we had before, except we have to keep track of the fact that it's half integer quantized. Okay. So product over m belonging to z plus half. 1 over q, 1 plus 1 minus q to the power n, okay, mod square. That is the term with the 1. And the term with the p is simply the same thing. m belonging to z to the power z plus half 1 over 1 minus 1 plus now mod. Yes.
In the first guy, why is there no contribution from states which were like, as Harshit said, the superposition states?
That's in Z free. In the second term, you mean?
In the first, oh, you have all of them
In Z free, everything is here.
with momentum.
Everything. Okay? This thing has nothing. Why does it have nothing? Because that changes P to minus P. And in that trace, you only get contributions if what you start with is what you end with. Okay? So you only get contributions from P equals 0. This is actually very similar to the way you get Bose statistics from a path integral. Do you know what I'm talking about? You can get Bose statistics by doing 1 plus P12 by 2. The half is just the usual thing. The second one, the P12, only gets contribution from states where both particles were in the same state. Because one was an n, the other was m. P12 changes it to m and n, and it doesn't contribute to the trace. Okay? But because the first guy got contributions from everything, there are contributions from here. It's just adding that extra factor of Bose statistics when two particles are in the same state. It's very similar to that.
I think you were asking about why don't we have a factor corresponding to momentum in the twisted sector.
We don't, because P goes to minus P. Sorry, I didn't understand. Twisted or untwisted?
In twisted sector.
Twisted sector. Twisted sector, there's no P at all. The oscillators are half integer content. I think what Chintan was asking was why, where do we see in the untwisted sector that you had momentum states? And that came in the first term.
I'm not actually seeing why don't we have momentum in the twisted sector.
Because the integers were half integer, mathematically because they were half integer quantities, there's just no zero mode. Okay? And physically, because the twisted sector lies around the origin.
Okay, the ends are fixed.
The ends are not fixed, but if one is here, the other is there.
Negative of
Center of
Overall, it can't move, right? Yeah, center of mass.
And I think you blend it with the ground state of this untwisted sector is invariant. Is that?
Oh yeah, ground state is invariant. Ground state is invariant. The state with one oscillator is not invariant. It depends on ground state with zero momentum is invariant. Okay, we better go. Yeah, let's continue next. Not at all.